Okay, this is 5.7 Exponential Equations, Changing Bases. And the objective will be to solve exponential equations and to change logarithms from one base to another. So here we go. All right, this is a great exponential equation right here, and you'll notice that we're a base 2 on the left and a base 8 on the right. All right, so with your laws of exponents, you know that if you can get common bases such as b to the x equals b to the y, that is true if and only if x equals y. So our goal here would be to get common bases, and 8 can be written as a base 2 number. So we'll leave the 2 to the t minus 3 power on the left, and on the right we're going to write that 8 as 2 to the third power. Now this statement can only be true, let me get that third power on there, if t minus 3 equals 3, because we have common bases on both sides. So t minus 3 equals 3, add 3 to both sides, and t equals 6. And that's all there is to it. Exponential equations, if you can get a common base on both sides, you just use your rule right here. B to the x equals b to the y if and only if x equals y. Okay, now this one's a little more complicated, but we can still do the same thing because we have base 3 on the left and base 9 on the right, and we can write a base number as a base 9 number as a base 3 number. So that 9 we're going to think of as a 3 squared, and then over here on the right we have a 3 to the first. And this cube root of 3 we're going to write with a rational exponent. That would be 3 to the 1/3. And now we are base 3 on both sides. On the left, power of a power. This would be 3 to the 4t power. And on the right, 3 to the first times 3 to the 1/3. We would add those exponents to get 3 to the 4/3. And now 3 to the 4t can only equal 3 to the 4/3 if 4t equals 4/3. Divide both sides by 4, and you get t equals 4 over 12, which we will reduce to 1/3. And that's exponential equations solving, getting same bases. In 1990, there were about 5.4 billion people in the world. If the population has been growing at a rate of 1.95% per year, estimate the year when the population will be 8 billion. All right, so this looks like a simple, interest, like a simple growth here. So simple interest, we're not talking interest here, but think of that formula like that. And that is your a of t equals a sub 0 times your growth factor of 1 plus r to the t power. Okay, so let's put in what we know. So a of t equals, and we're talking in 1990 there were 5.4 billion people in the world, so let's just call a sub 0 5.4. Okay, and then we have a growth rate of 1.95%, so we're going to go 1 plus, and then write 1.95% as a decimal by moving that decimal place 2 places to the left. So what would that be? 0.0195? 0.0195. There's my 1 plus my growth rate, my rate, and that's my growth factor right there. Okay, and we want to know when the population will become 8 billion. So let's put an 8 on the other side. Okay, so step 1 would be, let's divide both sides by that 5.4. So 8 divided by 5.4, and on my calculator I have 1.4815. And on the right, then I still have my growth factor, 1.0195 to the t power. Okay, and now we're solving an exponential equation. And to solve for that t, do you guys want to take the natural log of both sides? Natural log of 1.4815 would equal the natural log of 1.0195 to the t power. Now, with our laws of exponents, we can take, or laws of logarithms, excuse me, this exponent of t now can come out as a coefficient. So we have the natural log of 1.4815 would equal t times the natural log of 1.0195. Bring it out front just like that. And then t would be this natural log divided by the natural log on the right. So t is the natural log of 1.4815 divided by the natural log of 1.0195. Punch that out on your calculator very carefully, and this would approximately be 20.35 years. So the question was, estimate the year when the population will be 8 billion, and it was 5.4 billion in 1990, and we just said it's going to take approximately 20.35 years for the population to get to 8 billion, so that would make the year 2010. Approximately the year 2010. That's a cool problem. All right. Now, suppose you invest P dollars at an annual rate of 6%. Not bad. Compounded daily. That's even better. And you guys remember, daily is approximately continuous. So whenever I see daily, I'm going to use my continuous change model. Okay, continuous change. So that is P of t equals P sub 0 times e to the RT power. Just like that. Okay, so now, how long does it take A to increase your investment by 50%? So let's set up this equation. So my investment was P sub 0. And if I want to increase that by 50%, I want to end up with 1.5 times P sub 0. So I want to know when my continuous change model of P sub 0 e to the RT is going to give me 1.5 times P sub 0, or a 50% increase in my investment. Now, my first step would be, well, you have a common factor of P sub 0 on both sides now, so let's divide both sides by P sub 0. Oh, first, let's go ahead and put in our interest rate, okay? And that is what, 6%. So in the continuous change model, that has to come in as a decimal, 0.06. And there it is right there. Okay, now let's go ahead and divide by P sub 0. So we have e to the 0.06t power would equal 1.5. And now, if I want to solve for this t right here, that's an exponent, how about we just take the natural log of both sides? The natural log of e to the 0.06t equals the natural log of 1.5. Now in this case, the natural log and the base e exponential, those are inverses that undo each other because they have the same base. So that's just going to leave us on the left, our 0.06t equals the natural log of 1.5. So t would be the natural log of 1.5 divided by 0.06. And let's punch that out carefully on our calculator, and that will be approximately 6.76 years. So it's going to take almost 7 years for our investment to increase at 50% if we're getting 60% or 6% interest. Okay, now let's double our money. So now this P sub 0 e to the RT is going to have to equal 2 times P sub 0. And same thing, let's put in our rate and then divide both sides by that P sub 0. So I've got P sub 0 e to the 0.06t power equals 2 P sub 0. And dividing both sides by P sub 0 will give me e to the 0.06t equals 2. And one more time, let's just take the natural log of both sides. The natural log of e to the 0.06t, I could skip a step and go right to 0.06t. I don't think I did, but that's what I typically would do. And then the natural log of 2. Now, again, these are inverses. They undo each other. So on the left, I have that 0.06t. And on the right, I have my natural log of 2. Now let's divide both sides by that 0.06. T equals the natural log of 2 divided by 0.06. And I hope you guys are noticing something right here. Check it out. To increase our investment by 50%, look at this final answer right here. It's the natural log of 1.5 divided by what? My interest rate. To double my money, look at what we have here. The natural log of 2 divided by our interest rate. Wow. We use that a lot in calculus. Okay, so and let's punch that out. What's the natural log of 2 divided by 0.06? It's approximately 11.55, or almost 12 years. Okay, so 12 years to double my money. Actually, we're going to double our money in less than 12 years too. Now, there's another way we could have done this problem, because B, to double your money. Do you remember the rule of 72? Let's check it out with the rule of 72 and see if we get the same thing. So the rule of 72, if a quantity is growing at R% per year or month, then the doubling time is approximately 72 divided by R years or months, or whatever unit of time we're using. So let's take our 72, and our interest rate was 6%. Now here we just put in a 6, and what is 72 divided by 6? Look at that. 12. It's going to take 12 years to double our money. That rule of 72 might even be a little more efficient than the way we did it on the previous slide. Okay, anyway, let me get back there. Okay, the last thing on this lesson is the change of base formula, and I use this all of the time. I love it. It's very simple. If we have a log, a common log, or excuse me, I should say a log base b of c, I can answer that immediately with a calculator, and I use the change of base formula, and it's simply this. Now you can use any log, any bases in this, but I like to use natural logs. So I'm going to say the numerator becomes the natural log of c, and my denominator becomes the natural log of my base b. So the log base b of c will always equal the natural log of c over the natural log of b. Simple. So with that, I could do something like this, which I cannot do in my head. 5 to the what power is 8. I could approximate that, but I can't get a real good approximation in my head. But I can take out my calculator and simply go the natural log of 8 divided by the natural log of 5. And I'm going to do that right now on my calculator. Here we go. The natural log of 8 divided by the natural log of 5. And I hope you're doing this with me. I'm getting 1.292029674. So let's see what we rounded that to. How about a 1.29? That looks great. And that is how we use the change of base formula. Okay, I'd like you guys to do 5.7, 1 through 21 odd, and then 25, 27, 29, and then 37 through 40. And you guys have fun, get really good at this stuff, and get a hold of me if you need some help or have any questions. Have a great day.